fulfill. So, yesterday we discussed a special model, and let me just remind you. So, it's a scalar field on this deformed algebra. We got the derivations and so on. So, everything was quite simple. So, it's really one scalar field only, a trace. And the derivations were the bracket is x twiggle was just beta to the minus 1, theta had rank 4. That's a minor point actually, and I need it for the dimension already. It should be 1 over length, but it's simple, very simple. And so it's a Laplacian on this space. And well, we said yesterday, if we just take the naive terms, we don't get really a good answer. It's becoming non-renormalizable. And adding one more operator in the language of renormalization group, a relevant operator, this one, anti-commutator. So it's like putting the system into a box, but we will remove the box in half an hour or so. Then it's becoming not understandable. No. So that was the model, and I discussed how to say various aspects. It's becoming renormalizable, which in perturbation theory first, and therefore the idea was to go ahead. Now there are many motivations for this term. There's a paper by Axel de Goursac. I guess the title already has 3 motivations. So for instance, motivation comes from supergeometry. It goes to a super manifold and quantization. Another aspect comes from a term like curvature, by the way. And another aspect comes from a duality, which I didn't mention yesterday, which means a kind of Fourier transformation, which leaves these terms invariant and maps this term to this one, and vice versa. So if you would like to stay, it's a little bit like, you know, the bracket behind is, of course, well, you see it here. That's 4-dimensional, but if you stay 2 dimensions and call it xp, it's a standard stuff, and there's a map which leaves it invariant, x into p and p into minus x or so. That's more or less behind. And this duality maps this one into this one, and vice versa. Now, and I discussed that the flow of the coupling constant is fortunate for us. For instance, of the coupling constant as a function of the cutoff, we discussed, well, it starts somewhere. It would develop, the lambda ghost, and everything breaks down at a high energy, but anyway. And here it's bounded. Or omega, that's for the lambda, let's say. And the omega starts somewhere, and it's bounded 2, and it's bounded by 1. So the flow is squeezed while you start between 0 and 1. It never overshoots 1. Or you can start above and use this duality. Okay, then you stay above, but that's equally good. So it's a bounded flow. In the language of the physicists, that means the beta function is identically 0. So to say, the model makes sense at all scales, and the lambda need not be renormalized by an infinite amount. And that makes it, of course, much, much simpler. There are, of course, still divergences around. The mass will get a divergence, and I forgot, of course, to replace a phi, as we always do, by a scale times phi, and the scale would give me a z here, and a z square here. And z, of course, should also get the cutoff. So the cutoffs come, and there will be a cutoff on the trace, of course, so with finite dimensional matrices. That will have the cutoff, and I don't write always the cutoff. The omega flows anyway to 1, so let's assume, and let's afterwards prove, so to say. Well, I will not prove it directly, but we proved it non-perturbatively. So let's put it 1 to 1. So that makes much, much simpler the model. And what does the model become? That I write afterwards immediately down. So we've gotten only 2 constants. That's enough, especially in my age, I mean, to handle the flow of these 2 constants. And the question is, well, the partition functions, the appropriate partition function, and the correlation function, do they make sense? And, well, what are the properties? So to say, can we adjust the stuff to get a non-trivial model in the limit? That's, so to say, behind. Now, at omega equal 1, if I got everything right, I guess yes, even the signs, fortunate. You get x, you get 4 terms here, 4 terms here. But 4 from 2 from here cancel 2 from here. You see immediately, isn't it? X phi, X phi, X phi, X phi. So if omega equal 1, they are gone. So what remains, and using cyclicity, all the other terms 4 remain are the same. I'm sorry, I didn't write the 1/2, so that, so to say, was to wake you up. I'm sorry. Who gets it first? That is okay. So you get 4 times the same terms, and what do you really get? You get a trace. It becomes, well, at omega equal 1, a trace of Zn times, well, the x twiggle squared, phi squared, and 4 times, since mathematicians are around, so let's put a 2 even, but who cares? and all the others, okay? Now, what is this? And we called it all, we get a dynamically matrix model. It's not a good old of the matrix model type, which were discussed heavily by many people, connected also the strings and so on. It's a dynamically matrix model because it has gotten an external matrix here, which is a kind of Laplacian, but a bit simplified, as you see. I mean, a bit simplified. But I personally feel many things which come here could be done in the general case, but it's much more simple in this case, so to say. And what is it really? Well, it's 4 components squared Euclidean, but think of always 2 first and then double everything. So in the future, I will think always of 2 dimensions more or less, all right, and then you have to double everything, so that's trivial. In 2 dimensions, it's like x1 squared plus x2 squared, but they don't commute. It's like x squared plus p squared, the harmonic oscillator. So what is it? In the language, even I introduced at some time, it's a star a. So I will diagonalize this matrix that gives an integer. So, well, not one integer, we are in d equal 4, so we've gotten 2 integers, and they come immediately. So everything leads to a very simple question, matrix model, with partition function generating functional, which is what? Well, let's write first the J, and the external matrix E for external. So that's essentially this one. We will diagonalize, except for Firlefanz, some kind of constants and so on. And well, actually, it's finished, I guess, except for the cutoff. So it's a matrix model, d phi, n times n matrices, everything finite, e to the minus trace of the external matrix times phi square plus lambda, well, the 4 is due to cyclicity, phi to the 4th, and, okay, plus trace of j times phi. So, except for the small details, I'm sorry, like this one, what is E? I put the set here, but it's, and let's diagonalize it. That is to say, EAB is then, it's then a set, A plus B, the integers, Well, they are actually doubled integers, okay? Plus ms, and since there were constants around, let's put mu square. So mu square will flow, z will flow, and that's all. Now, okay, you can relax and try to think about it. A few remarks about this matrix model. It looks a bit like the Kontsevich model, which probably a number of people know. The point is, what is two-dimensional gravity? We heard about gravity in any dimension today. So it's very simple, and actually no dynamic degrees of freedom, so people say trivial, but it isn't. We have the genus, I mean the on the one hand, and we have the volume or area. So we have only two invariants, and to mimic it, so you sum over genera, and the area you triangulate. So you get to triangulations, to dynamical triangulations. So if it takes triangles equal size, and if the curvature is positive, you have more triangles, and if it's negative, and so on. So you come to a triangulation, you go to a dual lattice, and in the dual lattice, it's a partition function, which many people will know, e to the minus sum of alpha n trace m, the matrix, to the power n, and all the alphas, so to say, enter here. That's how you mimic, so to say, well, you know, or you go to a Liouville theory and follow Polyakov and so on. Anyway, so that would be the stuff, and Witten conjectured that this expansion in large N is comparable to a partition function of what we call Kontsevich model also, and which is what? Well, dm e to the minus an external, sorry, a trace, of course, an external matrix times phi plus I phi cube. Okay? Array function. Sorry? Matrix array function, exactly. Yeah? Now, and the main thing is, of course, how is it related to the above? What are the relations? And the point is the constants are, except for, well, constants which seem to be 2n minus n double faculty, but I guess it's okay. The trace of e to the minus 2n plus 1. So you see there's a one-to-one relation between these constants and these constants, and so to say everything is combined in one matrix model, so that kind of two-dimensional gravity is, well, of course, that's not so easy to go ahead, so we've completely independent develop this kind of thing, of course motivated by stability. I mean, therefore there's I, because of course that's a different story, develop and try to analytical continue in a certain complex constant lambda afterwards. Now, that's just a, yeah. Oh, very good, yeah. Thanks a lot, yeah, of course. Yeah, well, that's the point. There are two versions, actually. Yeah, right, thank you. There are two versions. You see, the comparison is, of course, much better with a phi square, but there's a trivial transformation, a shift, so everybody can find the shift to a new phi, which is the old phi plus a constant, whatever it is. It's heavily, whatever, I don't work it out, e over, and so on, some constant, such that you get a linear term, right? Okay, that's here the point. This array function business might start like this one or like this one, and that's a trivial shift which is completely irrelevant in the game afterwards. Yeah. Okay, now, so how do we go ahead? This one? This? n times n matrices. Real matrices. Yeah, n real or complex Hermitian matrices. Yeah, right. N times n matrices. That's exactly the point now. The next point is, of course, essentially how to go on. Ward identities and Schwinger-Dyson equations. So to say, equations of motions. And Ward identities, symmetries. And okay, everything historically, I don't make too many comments now. What is exactly the point is now we make a transformation, the phi into u, phi, u star, and observe, where is it? Oh, yes, phi squared times mu squared, m as a constant, is of course invariant. Phi to the fourth is invariant under the transformation. This is not invariant, so observe it. And what is not invariant is this one, of course. I mean, the first, this part. Now, but the measure is invariant, so we get an equation of the following type. Which turned out to be very essential and very strong. Well, e to the minus, I didn't give a name, but maybe I give a name. This one is a kind of action with J, E, and phi. Action is J, E, and phi. Times. Now you make an infinitesimal expansion, and from here you get, of course, E, the commutator of E times phi squared, minus phi square E. And this should be compensated by the change of J, which means J, phi minus phi J. Now, maybe I make indices. I'm sorry, that's a metric, so I make indices A, N, N, B. Otherwise, I will make an error immediately. N, B, A, N, N, B, A, N, N, B. Now, what does it mean? And to simplify my life, and your life hopefully too, I make it graphically. That's an insertion of an operator, a composite operator phi square. It has gotten a set, by the way, from here. And then here we observe, well, that has a part A plus N plus mu square. And this one has a part N plus B plus mu square, but there's a minus in between, so the mu square terms drop. So what remains is the following. Z times A minus B, that goes out, times, and now comes an expectation value of what? Well, this composite operator, Z times sum over N, phi A N, phi N B, times phi, well, now comes everything. You can differentiate any times by with respect to J, so you get all the correlations, B, blah, 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 and A. Equal, well, and this is a kind of angular momentum. It kills one index and creates another index of the partition function. So it makes what? It makes, here we are, phi of, well, the sign, I don't know exactly, but any A point, it makes a B into an A. So it gives this one minus a correlation phi B. Phi B. Or maybe really graphically, it was not graphically, I'm sorry. You can see it better than me. It means the following. Z times A minus B. Actually, I should say, well, my graphics is, of course, a bit cheating in the sense the fine details were elaborated on. But the graphics you can bring to the public. You see, you have to be very careful about details. But I like, nevertheless, to present it, because otherwise the formula are very heavy. And I didn't prepare like Masood in the morning. So that means A, and there is a kind of N, I guess I called it NB. This insertion means this composite operator. And, well, that's anything. And that starts with A. I mean, I'm sorry, maybe I should have told you. For omega equal 1, these rules of the matrix model, I mean, are really simple. The lines have to go on. So that means this line really goes here. It cannot jump anymore. That was the effect, that the terms were killed which jumped typically. And here's anything, and here B ends. So that means this one is what? Well, now it's easy. It's A, anything A, minus. Because, I mean, you are very kind and silent, but you should be very nervous. How to say? That's deep for me, at least, when I saw it in a paper by the Paris group. A 4-point function is related to the difference of two 2-point functions. That's very rare in my age. I mean, look. Okay. Now we go to Schwinger-Dyson equation. Schwinger-Dyson equation is in principle terrible for n equal 2, of course, only. And we go to one particle irreducible part. So from the GAB, you see there could be one particle irreducible part, which are the graphs. If you cut, they don't decay. And you can repeat it and sum it up. So that's this formula which goes like what? Z to the A plus B plus mu square minus gamma AB to the minus 1. Okay? And if you, that's the one particle irreducible, then blah, 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 you expand. So that's summed up. So let's go to gamma AB. And gamma AB now means the external legs are taken away. So we start with 2-point function, which means one particle irreducible part with, well, symbolically, the A comes here and the B comes here. Now, what is it? A, B. Either it has a left dipole, if it comes like this, and particle, it's got a left dipole, oops, and some interactions here. Maybe otherwise I forget. That has, of course, a z square, a lambda, the vertex here. And then, yes, let's make a P. So we have gotten a G, a P, summed over P. Well, that's, of course, gamma AB. That should be an equation, finally. Now, plus, and here we have the other dipole. 2-point function, plus, and now comes the point. I mean, that's the tragedy. For us, not fortunate. It's a 4-point function. A, B, insertion, something like insertion. And yes, okay, well, I don't know, P, Q. So you see, I don't recommend to enter this stuff. It's terrible. I mean, our stuff, it's nice, but in commutative field theory, a 2-point function is a 4-point function. A 4-point function given a 6-point function, it never ends. In statistical physics, it's called the BBGKY hierarchy, and here's, okay, hierarchy of Schwinger functions. Well, there are strong people who are doing it, I mean, from time to time, but not me. Now, but you see, still, here it is. There's some hope when we saw it first. We thought, well, what's the relation between these two things? There is a relation. So relation to Ward identity, or better saying, how can you use the Ward identity to get an equation for the 2-point function separate? That's the goal, and that the goal, well, I sketch a little bit. How to say, yeah, we try. But I have to slow down, otherwise I make too many errors. Yeah, no. So, yes. So that should be the A. And oh, I forgot the full, the Reimer is too kind to me. The full green function is meant here. Here, I got it, yeah. A, P, Q, Q, A, P probably. I hope, at least. So, okay. Now you see it's not identical. Well, in addition, there is, of course, a graph which corresponds to this one. Therefore, this one is easy, and these two we combine, but that's a minor point, so I don't P, there's a P running, and the B, it jumps. This we had. Now, you see, how is it comparable? Well, first of all, this one is not so welcomed. Well, here I forgot anyway already. This is not welcomed, but that's GAB to the -1. So we shouldn't forget, finally, okay? We truncate it to account this lag, which is taken away. Now, next, it's almost the same. You have to bend this to the other side and sum over Q. So in effect, while the vertex is NZ fits here too, Z times lambda squared on the one hand. And then maybe I do immediately combine this using the Wood identity, because now I can use the Wood identity. So what will I end up? I will end up, first I shouldn't forget the inverse, AB, I mean, for both, take it away. Sum over P, but here I made a little error, because that seems to be the Q, and that has to be the same index, of course, because I would like to sum over P first. And then you see that's the insertion, so that's will give you finally, well, these two make a kind of Z times, oops, now it's A minus P times the insertion over Q, phi AQ, phi QP, and all the two others, okay? And that gives you, of course, a G, oops, what is it? G PA, PB minus GAB over GP minus A. Now, what you end up should be of the following form. Well, here it's a one-particle irreducible part, so we go ahead and write here minus GAB to the -1 and a set A plus B plus mu square from the equation you see. Now I multiply everything, which should be written here, times GAB and divide by set A plus B plus mu square, and let's see whether it's almost the last essential formula, which you should understand up to this point. So what will it become? It will become the Green's function, which comes, well, this one is killed, but this one we kill, so we get from here GAB is equal to the free one. We divide through the free one. Then there is the dead ball, the beast, so to say, Z lambda over A plus B plus mu square, GAP sum over P GAB, the beast because it makes it nonlinear, plus Z square lambda from the vertex, somewhere, here we are, I don't know where I wrote it, yeah, here we are. This one is killed, and here something develops which is, to my opinion, incredible, surprising. It's one equation for the 2-point function. So I will not write it for the 4-point function. This develops into a kind of nonlinear singular integral equation, which I will say a little bit about it. For the 4-point function, I can tell you immediately, it gives a linear inhomogeneous integral equation, and for 6-point, again and again and again. So that is very surprising. So this easy. The complicated beast is this one. So we have to renormalize first. I wanted to say the great thing is with this we decoupled all the Schwinger functions, this hierarchy. The bad thing is, at this moment, it's completely without any value. Why? nothing has a limit. We have to renormalize. I mean, of course, there was a question. I mean, everywhere my n, I'm sorry for this. Here not. We hope for the best. The beta function is 0, so it should flow to whatever it is, yeah, a finite value. But everywhere, here is an n, here is an n, well, and so on. Not many n's, but, and of course here, and so on. Unrenormalized. All the bare quantities. I'm sorry now. Did I get all of them? Yeah. No. Anyway. Now the question is, so then can you adjust the flow for these two parameters such that you can extend these limits and get probably integral equation? I mumbled it already. Renormalize. Now, if you think about it, in gamma AB, somewhere written above, there is already the A plus B plus mu square linearly entering, and also the Z. So that's much better. And you can renormalize for these terms in the following sense. We subtract from this unrenormalized quantity this one and get instead the renormalized one. We subtract from the left A plus B times Z. So to say here, the mu square. Oops, I'm sorry, that is an error, of course. And Z times A plus B. But we add A plus B, and we get the renormalized AB plus conditions. That's always, if something would logarithmically diverge, I take the difference, and the difference has a limit. That's really built in. Oh, I'm sorry here. Plus conditions, gamma 0, 0 should be 0. Non-perturbatively, d derivative in one direction, 0, 0 should be 0. Now, well, now comes the point which I don't write, which means you have gotten 3 equations now. This one, you write down from this one, and this, of course. 3 equations. Eliminate Z and mu square in terms of the renormalized ones. That's so to say. Now what do you get? Now, and then take limit. You see there are 2 cutoffs, a volume cutoff and an UV cutoff. In the morning, you remember. Volume cutoff and lambda and the momentum cutoff. Now, in work by Victor Garal and Reimer, they studied the spectral geometry of a Dirac operator in this kind of deformed space and got that the volume goes like zeta square. Very natural, because you have a discrete spectrum, it's a finite volume spectral geometry, okay? You're mathematicians, you buy this limit. We take the strong deformation limit, h bar going to infinity. I mean, not really h bar. But anyway, you see, I personally, I am very happy if I have a non-trivial model. It's a bit artificial in some sense, physically speaking, maybe strong deformation, not weak, I mean, for nature, so to say. But who cares? I mean, now, and in addition, what is this? So, yeah. In addition, n, we have, of course, a cutoff. Over theta, we keep constant and take to be lambda squared times a constant, and takes a limit here, and to theta, and theta going to infinity. Though that's a thermodynamic limit. So we remove the box, and since, it's even written here above, the x wiggles are have gotten a 1 over theta, so actually omega over theta enters, and we put theta to infinity, so it disappears again. We remove the box. Okay, I mean, yes, it's in this spectroscopy, it's very natural, actually. Huh? Now, what do you get? Well, of course, I cannot, I could write, but these are too many formulas. I mean, it's like the emperor in Austria once heard a new Mozart symphony, and he was sleeping away, and afterwards they waked him up and asked him, how did you like it? And he said, too many tons. So too many formulas, otherwise, I'm sorry. Okay, otherwise too many formulas. But you can imagine you take these three equations, manipulate them so that eliminate the z and the mu square, take the limit carefully, and what do you get? For GAB, you get the nonlinear equation, which are almost right afterwards. Nonlinear singular integral equation. I can write, of course, more or less, of the Kalemann type. In the Russian literature, it's called Mushkelishvili type. I could also say, well, when I was very, very young, I did almost the same, but with linear integral equations, but in 2 dimensions. That's the effect of 4 dimensions, the dead pole. I mean, the singularity. It's a quadratic singularity round. In 2 dimensions, much, much simpler. Almost all probably all models are much, much simpler than this one, I have to admit. But of course, 4 dimensions are really much more tricky. A quadratic divergence. And the logarithmic, of course. I mean, that's the point. Well, the logarithmic. Now, okay. And so this Kalemann or Mushkelishvili literature is quite old. And we were stuck for I don't know how long. But Reimer had a brilliant idea after some time. And this idea was to, well, of course, we played this way, that way, what you do with the nonlinear equations. Actually, it seems to be not treated in the literature. I mean, for the linear case, yes, there are books, of course, books by these people. So to say, from the mathematical rigor side, I would say, we define our model this way, of course. I mean, up to this point with cutoff, everything was well defined. Now it takes a limit. And of course, I mean, it's hard to see. By the way, Hölder continuous functions are appropriate for these singular integral equations. And we search for a solution within this, okay, equation. Now, the brilliant idea was GAB minus, I mean, the brilliant idea we can say before already. Assume GA0 is given. I mean, we played all kinds of subtractions, this equation with an equation where we put something 0 and so on. But we never thought about this one. Assume this is given. Evaluate the full Green's function. So assume the Green's function is, so to say, given at a certain value. I mean, there is an A and a B. These are double indices, but only the sums occur for the 4-dimensional case. Assume this one is given. Can we get it everywhere? Okay. Now, oh yeah, there's a minus, yeah, of course. GA0 over B. So the difference of this type fulfills a linear integral equation. Maybe this one, we have still time. Oh, but I should hurry up to tell you. So this is given. 1 plus lambda A. Hilbert transform. Do I have to define the Hilbert transform? No. I guess no. This one times DAB minus lambda. Hilbert transform in A of D of dot B equals minus GA0. Now this equation, I'm sorry, I prepared even for students to tell you the strategy, can be solved by going to a Riemann-Hilbert problem. And this Riemann-Hilbert problem is solvable. It's not completely trivial, but so for a class of continuous functions here, well, that's in terms of A. B is a spectator. This kind of operator where the Hilbert transform is just the integral over dx, x minus, well, what is external of the, well, this dot stands for x, dxb. And that's a solvable Riemann-Hilbert problem, so you can get an explicit solution for GAB in terms of GA0. But you know it has to be symmetric, so you go here. And that's a consistency condition for GA. So to say GA0 has to be, of course, G0A, and that's a nonlinear equation, which first of all, we know it has a solution from a fixed point theorem. There exists a solution. The computer tells us what the solution is. It's monotonic decaying. It's smooth. it's convex, but we don't know exactly. I mean, it's a highly complicated nonlinear equation. So this equation, the solution of this equation is something we are doing every day here. Fortunate. Thanks for the invitation. But that is not completely finished. The computer finished, of course, as you see. Now, modulo this function, but as I said, the existence is proven. Everything becomes now algebraic. So GAB is a complicated expression, this one. Go to the 4-point function, do the same. What comes is a funny relation, which is easy to write in public even. GABC, A minus D, B minus C. And that goes on. So for the 6-point function, you can guess. I don't write it, it's lambda squared times 5 different contributions. And the different contributions can be encoded in terms of so-called chord diagrams. 2, 4, 5. Which means, well, we take the 6 points. And that's symbolically for always products of 3 of the, that's an A, that's a B, C, D, E, F. I'm sorry, A1, A2, and so on. 3, 4, 5, 6. And so on. So oops, just this one will not enter anymore. and the others, I mean, this one, and so on. And so on. So that's all algebraic, and I'm sorry, depending on time, I am quite sloppy now, and I admit, I'm sorry, because in this limit which I mentioned, I forgot to tell you, this limit is very special in the sense it maps to genus 0, but the number of boundary components can be anything. It's a limit which was not so much discussed in the literature. It's a kind of Swiss cheese limit. So the topology is a Swiss cheese with number of holes but no handles. Okay, so okay, everybody can imagine. So and all what I said, this hierarchy, which is algebraic, is for b equal 1. Now comes b equal 2, but time is running. So b equal 2 is, of course, as I have drawn more or less yesterday already. Now there are contributions. Well, where the 4 legs, for instance, for the 4-point function is like this, or 2 are here and 2 are here, for instance, okay? For 6-point function, of course, you can go up to b equals 3, and this, how to say, the strategy is again the same, except it's becoming more and more tricky and not completely worked out. So, final comments. We are first of all convinced it's becoming a non-trivial field theory. Well. but we didn't calculate the S matrix. Because just this one, I mean, you have to go up to the 6-point function, of course, to prove, no, up to the 4-point function for the S matrix, but to prove factorization, for instance, we have to go to here. But okay, also this one is not fully finished. Yeah, even trimester is finite, so, and the day has only 24 hours. So that's a pity, but that's on our agenda, of course. Now, what about, we made a lot of progress in solving the nonlinear equation, which I could write down, of course, but I didn't. Because having, you see, of course, everybody can say, if I know it's a solution, so maybe unicity, we work a little bit more and get unicity. But that's not the point. We would like to go finally to the axioms. And for the axioms, we have to go to, have to know the analyticity stuff and Stiltius property, for instance. And to know explicitly the solution, of course, it's much easier afterwards. But we are very close. I mean, to have Stiltius property of this function, and that would hopefully sooner or later go further to the so what are the OS axioms? Well, the first one is of course simple to estimate. It's regularity. What was the second? Well, whatever you order it. Euclidean invariance is automatically in this limit. That's the point. We introduced cutoffs, but in this limit it's becoming Euclidean invariant. So Euclidean invariant is okay. Now, well, the reflection positivity, actually, I mean, to tell you the truth, we know for lambda positive it's violated. Actually, the computer knows, and Reimer, of course. For lambda negative and small, there is a lambda critical, where it will break down, the computer knows, a phase transition. But for this one, we have not only great hope, I think a trimester should be enough. Well, OS answer 5, I'm not now too much in a heat state. So anyway, clustering is violated, by the way. But clustering is not such a deep thing because you decompose into pure states also. I mean, I'm not telling you that I am able to do it explicitly. What is missing? Symmetry is okay. Well, but that's Euclidean. I'm sorry, yeah, no, of course. Thank you very much, of course. Locality is fulfilled. Locality, which is so essential. Yeah, sure, thank you very much. We don't worry about it, it's coming out, yeah. So that's more or less the end of the story, except, well, it's never ending because you can ask 100 questions. You see, it's something which is almost an integrable system from many aspects, but I cannot prove these aspects rigorously. In the sense of where are the conserved quantities, where is I don't know. I didn't tell you. Oh, I'm sorry. The Kontsevich model is of course connected to the KdV flow, so and KP hierarchy. So well, but here it's not immediately seen. Nevertheless, for instance, this algebraic hierarchy of m-point function, etc., etc. By the way, our momenta are kind restricted almost like in 2 dimensions in the sense the set of incoming momenta has to be equal to the set of outcoming momenta. So it's a toy model in this sense. It's not the reality, but who cares? I mean, if you have a non-trivial model, you know, we are, I feel like, like Bethe or Walter Thierring or so, all these models were at the beginning. And it's the first model in 4 dimensions. I mean, the dimensions are there, that we are sure. So, okay, thank you very much for your attention and for the workshop in general. Yeah. Oh, you could take. you could take, of course, in the box. You see, yeah. I mean, four-dimensional. You see, we have a box. So it's a little bit. It's an infrared cutoff. So yes. Oh, that might be. Yes, of course, a quantization in the sense because of boundary conditions. Yeah. Otherwise, you have. Yeah. Yes. It would be like the modules, you know, Pimsner-Volkodesko, they had also a Kettenbruchentwicklung, the approximation with finite, yeah. Ooh, good question. Is it non-explicit? It's explicit. For the two-point function, yes. Yes, I would say yes. Mm-hmm.
I'm getting at the point that, of course, reflection positivity guarantees the continuation.
Yes. As that you really have a handle on how to do it explicitly, yeah. Yeah, well, one thing is, for instance, for negative lambda, you see, we see an essential singularity at lambda equals 0, by the way. Yes? So for negative lambda, it's much better behaving. Since you worked how many years ago on the Turing model, the propagator is behaving like 1 or mass asymptotically, p square to the power 1 plus lambda, so plus and so on. And that is a problem. I mean, if lambda is positive, it's a too high power, and that violates reflection positivity. So, yeah, sure, right, yeah. Uh-huh. Ah.